and welcome to the February IXPUG Technical Webinar. Today's presenter is Steffen Christgau from ZIB in Germany, and he'll be presenting on the topic of migrating from Cuda only to multi-platform data parallel C++. Also joining Steffen during the Q&A that we'll hold at the end is Marius Knaust, also from ZIB. Steffen, please begin.
Yeah, thank you, Shari, for this kind introduction. So I'm at ZIB, the Zuse Institute in Berlin here. I'm a research associate at the Supercomputing Department. And part of this work was done within the context of the Research Campus Modal in our HPC lab here at ZIB, which is funded by the German Ministry of Education and Science. So Shari already gave you the talk, the title of my talk. So here's the agenda, if everything would work. Yes, now. So the agenda is basically we have a short look on the motivation why we are looking at migrating from Cuda to data parallel C++. And in particular in this talk, we have a look on the application named easyWave, and we will have a closer look on what it is doing and how is the source code actually looking like. And then we have the main part of this talk, which is how we can migrate from Cuda to one API. Where are the differences? Where are the challenges? And how can we be more SYCL-esque, as I will call it in this talk. And in the ending, we will have a look on how we can actually use different architectures with our migrated code. And obviously, there's also the conclusion in this talk. So for the motivation, I think most of you, if not all, know that heterogeneous architectures are kind of the way to go to be both energy efficient and have increasing or large computational power within the next years, decades, I don't know. But you also may know that there are special purpose architectures which are well suited to particular tasks, like, for example, you have GPUs which are well suited for data parallelism. You may have specialized vector processors or accelerators. You may have FPGAs, which you program on your own, or you even have ASICs, which are well bound to a particular use case, like, for example, these tensor processing units, which are used a lot of in machine learning applications and AI applications. However, the challenge here is that your programming environment for heterogeneous architectures platforms may look kind of diverse. You have a large diversity of architectures, as I showed you, and you also have a large diversity of programming language or standards which can help you or which allow you to program these architectures. Some of them are proprietary, so bound to a particular vendor. Like, for example, Cuda is basically only available for NVIDIA hardware. OpenACC started only for Cuda hardware. Now things are changing, but yeah, you have these bonding to vendors and their hardware when it comes to their preferred programming environment or programming language. On the other hand, you may have exotic ways of programming these devices. Like for FPGAs, you have Ph.D. and Verilog, and it's quite hard to program them if you're not an expert. All in all, you have almost in every application that supports different accelerators or different heterogeneous platforms, different code bases that support these different devices. Even for the same class, you may have different ways to program these devices. For example, for GPUs, you have Cuda, or you use Thrust or similar libraries to program GPUs. So as I said, you have this bonding between a hardware and programming environment, and the question is how we can actually break this bonding, so to say. And there comes one API on the stage, which, if you look on its website, promise you a common developer experience across accelerator architectures. And as a programming language of choice, you have data parallel C++ in one API, which is essentially C++ plus SYCL plus some extensions, which maybe not are extensions anymore, since we have a new SYCL standard for a few days. But from the statement above, you may get the expectation that you can run a single code base on different platforms like CPUs or accelerators that I have shown you before. And the challenge now is how you can migrate from your existing code base that is bound to a particular vendor, like for CUDA codes that is bound to NVIDIA devices, how you can migrate from there to a DPC++ code and gain, hopefully, support for multiple architectures. So, and then the question is actually how many architectures or which architectures are supported by the new DPC++ code that I gained from my migration. And in addition to that, you can ask yourself, can I still reuse my already purchased hardware? So in this case, NVIDIA hardware. And in this talk, as I said, we will have a closer look on easyWave, an application which we had used as a case study here. And easyWave is an application that was developed by the German Research Center for Geosciences originally, and then it was brought to the GPU by the University of Potsdam in a close collaboration. And what this application does is it computes the propagation of a wave on the ocean, so a tsunami wave, in case of a seismic event. And this is all done within the context of early warning systems or early warning processes. So in case of a seismic event, you are interested in an early warning center if your region that you are responsible for in the coastline is impacted, and how much it is probably impacted by a tsunami that is maybe just happening now. Therefore, you need a very fast computation, since you are doing parameter studies maybe to judge on the potential impact on your area you are responsible for. Therefore, easyWave was written, and it uses memory-bound stencil kernels that you often found in data parallel applications written in Cuda. And one interesting thing is here that the computation is originally limited to a particular area of the ocean where the seismic event occurred, and over the time, the compute domain expands over the area where the wave actually has propagated. And the easyWave code supports both Cuda and OpenMP. So it is written in C++, and to gain the support for these two different kind of devices. So for OpenMP, we have only CPU support here. For Cuda, you have obviously support for NVIDIA GPUs. You have different classes to do to get this support for these different architectures. So you have two different code passes in your code base that are responsible for doing the computation, which is kind of bad. If you adjust your model and you adjust your computation, you have to always maintain these two code bases. But maybe this changes with one API and data parallel C++. Now we have a closer look on how easyWave looks like, and I think it shares a lot of similarities with code that maybe you are aware of. So typical things here are that you allocate memory on your host device, so on your host for the GPU. For example, you can have two-dimensional arrays, which is obviously the case for easyWave here. And then you use according methods or functions from the Cuda toolkit or from the Cuda API to allocate two-dimensional memories. In addition, you have a thread and block-oriented kernel execution. So you specify how many threads you will execute per block, which maps to streaming multiprocessors, as you may know. And then you actually invoke the kernel in a function call-like pattern with this strange little syntax here with blocks and threads specified for the actual execution. And if you want to time your kernel, you may use this as well to have a Cuda event record before and after the kernel to actually do timing of the kernel here, to bring it in a nutshell. And on the host side, I think this is kind of typical, and on the device side, you again have kind of typical kernel here. You determine where you are computing actually in your overall grid. So with these implicit variables named block IDX and block dim, you compute where your kernel instance is actually computing on, so to say, and then you use pointers that you created on the on the host side, and you may transfer them with explicit memory copy operations to the GPU. So the data that is used under the hood, and then you use the pointers to access the data that you copied over to the GPU. So you have pointer-based access, and I think most of you are used to this way to program kernels. And overall, as I said, the kernels are stencils, and I think most of you know how stencils look like, and this is only a particular example here from easyWave. But I want to show you that typically you have this kind of code base inside your code maybe, and this is also the case for easyWave here. So now, how can we migrate actually from our existing Cuda code base to one API? And here you have two possibilities basically. You can obviously go ahead and rewrite your whole code base on your own, which might be kind of tedious for you. And on the other hand, you can luckily use the tool-supported migration process. And for that, the base toolkit of one API provides you with a so-called Compatibility Tool, or DPCT, which is the name on the command line. And DPCT, or the Compatibility Tool, provides you a convenient migration assistance. It won't do magically everything for you, but it's really a good assistance, as I have written on the slide here. What you do with a Compatibility Tool is that you put in your Cuda code base into this tool, and then the migration process is started and the output is migrated code. Although it is a process that is done by a machine, you get code out of it that is still readable and maintainable, and this makes sense because the objective for the Compatibility Tool from our point of view is that you get a good starting point for further optimizations and code adjustments. So the Compatibility Tool relieves you basically from doing all the manual and tedious boilerplate and syntax changes, and it also respects changes within the different programming environments. So differences between Cuda and SYCL or DPC++ are automatically covered to some extent. However, it may have some limitations. Sorry, but as I said, it's a good starting point to go ahead and tune your code afterwards, and relieves you, as I said, from this tedious task of changing syntaxes and so on. So actually, how does the migration process looks like? There are, again, basically two possibilities. The first possibility is that you can intercept your build process. So if you have a code base that uses tools like Make for building the code, you can intercept this process with the intercept build command or tool here, which basically records what the compilers do on the files with which flags and so on and so on. And this generates a file, and you only need the Cuda headers to be present on your system. You don't have to have a full installation of Cuda. The headers are sufficient enough for this step here. And this is a general requirement. So you only have to have the Cuda headers independent of the way you do the actual migration process. However, you need to check if your Cuda headers are really supported and refer to the documentation of the Compatibility Tool if your Cuda version that you have is actually supported. However, with the outcome of this first step, you get a compilation database, and this compilation database can then use as an input for the actual migration process. And then you can specify some other options, but basically the compilation database is essential if you do the migration in this way. However, you have another option. You can also migrate your code base file by file, and if your code base is larger, this might be the better way to do this, since you can check what is done on a file per file base, and you are not overwhelmed by all the changes that are made by the Compatibility Tool in your code base. And within the next slides, we will have a closer look on what the Compatibility Tool is actually doing with your existing Cuda code base. And as I said, we do this in the context of easyWave, as I said, a typical stencil application. And we will have a closer look on the subtle differences between Cuda and SYCL here on data power C++. And let's start with how devices are actually handled. So in Cuda, if you do a run or write your Cuda application, you usually don't care. I think most of the code that are only aware of a single CPU, single GPU, and they are aware of multiple GPUs in general. And you are not faced with handling a particular device in general if you write your Cuda application. If you use different devices, you have to use a function call that is named Cuda set device to switch between devices. Otherwise, so as I said, in most applications, you have kind of an implicit GPU you are acting with, and you are only acting with a GPU here. So there's always, obviously, an NVIDIA GPU you are acting here with, but the things are different in SYCL. And for easyWave, actually, we didn't use, don't have support for multiple GPUs in this version that is publicly available. So there you don't find CUDA set device calls. However, if you look at how SYCL and data power C++ handle devices or acting with devices, you find that you have to do this by means of a queue. So you always, basically for all operations that you're doing with a device, be it a CPU, an FPGA, or a GPU, you have to use a queue object. And with that, you can handle devices of arbitrary type. So it doesn't matter if you have a GPU. You can specify that you want to explicitly use a GPU or CPUs, but you don't have to. And if you don't do this, then your code is, I think, more portable. So it will run on different architectures. So for the code that comes out that is generated by the Compatibility Tool, you have basically these two lines, as I have shown you in the slide. You get the current device that is predetermined by the runtime, and then you can get the default queue. However, you are not limited to that. You can also specify that you want to use another queue and want to select another device, for example, in a SYCL compliant way, without this namespace from the Compatibility Tool here. And the nice thing is that if you use it in the way that is shown here on the slide, you can basically control which device you are using at runtime by specifying or changing an environment variable. And thereby you get already support for multiple devices, which is different from CUDA, where you only have support for CUDA devices. However, as I said, basically all operations that you are doing on the device are done with a queue, and this also applies to memory management and launching kernels and so on. And we will have a closer look on how memory is handled here in CUDA and in SYCL. So in CUDA, you basically have explicit allocations of memory, and if you don't use CUDA unified memory, you also have to do explicit transfers between the host and device, usually. And out of the memory allocation, you get pointers for your device data. And as we have seen in the source code of easyWave, you usually pass these pointers to the kernels and operate on these pointers. And for allocations, you usually have these CUDA malloc calls, and you say how many items you want to have for a particular data type, and you get a pointer out of it. For SYCL or DPC++, things are kind of similar since a few weeks or a few days, at least officially. So since I think beginning of February, we have officially released the SYCL 2020 standard, which includes a new concept that is named unified shared memory. And with that, you actually get a way to program in SYCL or data power C++ in a very similar fashion like you do in CUDA. So you have pointers, and you can have explicit memory transfers, which are again associated with a queue, as I hopefully made clear in the previous slide. And with that, you can also allocate memory like you basically are used to from CUDA or C, if you're a friend of C. And you get out of pointer here if you do an operation like a SYCL malloc device with data type and so on, and with a Q object. And you can pass this pointer here to your kernel and use this pointer there for other operations. This doesn't mean that the pointer is valid here on the, so you can actually access data with this device pointer from the host, but you can pass this device pointer to the kernel, and on the device side, you can access the memory that is behind this pointer here. So overall, this is very similar to what you're used to in Cuda and C, and it is very good if you're new to SYCL to have this concept here. So you can, as I said, use pointers and kernels and so on. However, this is actually quite different from what was originally written or specified in the SYCL standard, where you have buffers and accessors, which are basically separating things. So you have buffers for memory management, so to say, and holding data, and then you have accessors which are used, as their name suggests, to access the data. However, this is, from my personal point of view, kind of tedious to use. And it makes code quite verbose. And with a unified shared memory, you now have the opportunity to write code in a similar fashion that you are used to in C or even Cuda. But in the end, it's kind of a personal preference. But using a unified shared memory here is a good thing, since the code doesn't look much different from what the original code looks like. And you can easily spot differences and maybe even errors that are produced here in case your code is more complex. When it comes to kernels and their invocation, we have seen in the example, and if you're a Cuda developer, you are well aware of this, that you basically invoke a kernel like a function call here, with this, as I said, strange little syntax with this blocks and threads. And it is an implicit invocation, implicit data power invocation of a kernel function. So what you specify here is so-called execution environments that specifies how many blocks and threads you want to use for your kernel here. And as you may know from Cuda as well, is that kernel execution is asynchronous with respect to the host. So this function call does not block until your kernel is actually executed or finished. So you have to do other things to ensure this. The kernel invocation and the execution looks a little bit different in SYCL or DPC++. So what you do here is you submit a so-called command group, again with the help of with a requirement that you have to use a queue object here. And so you basically submit work to that queue. And that work is specified in a so-called command group, and that usually contains the kernel invocation. However, the kernel invocation is more, from my point of view, a little bit more explicit, since you specify that you want to operate or do a parallel for operation here. And also the specification of how your kernel is executed with how many instances is a little bit different. We will have a closer look on this in the next slide. But similar to Cuda, this submission is synchronous on the host, but the execution of the kernel is again asynchronous with respect to the host. So you don't know if your submit call returns that your kernel has actually started or even finished. So there are again other means to ensure this, and we will have a look at this as well. So when it comes to the execution of the kernels, you have the assurance from the Cuda runtime that if you submit kernels in a so-called stream, within the same stream, you have these kernels are executed in the order of submissions. So by default, you don't specify streams, and then you operate on a so-called default stream, and so you don't are aware of this maybe. So, but if you execute or launch kernels, then they are executed on the device side in the order you launch them within that particular stream. And if you want to, you can specify events for handling dependencies. within the stream, which doesn't really make sense, but between multiple streams, you can also use events for ensuring dependency management here. In SYCL, there's again a little bit of a difference. Queues in SYCL and DPC++, as it is only SYCL plus extension, so to say, queues are out of order by default. So if you submit a kernel and another kernel after that, you cannot be sure that the order is really maintained. So in the older SYCL standard, this was kind of ensured if you used accessors, which was the only way to access memory, if you don't have extensions. And then the runtime was able to determine the dependencies between kernels that have been issued to a particular queue. However, with unified shared memory, where you only have pointers, the runtime is not able to do so. So you need other ways to specify that you have to wait for a particular kernel to finish before the other one can execute. And the compatibility tool keeps the order of execution by by issuing wait calls on the queue. So basically, you get an event out of a kernel submission in SYCL, and then you can wait on that event, which ensures that the kernel has been executed. And then the next kernel can be launched. So in that way, the order is kept. That might be not optimal, but it keeps the ways, the things as they are in CUDA, so to say. So in that way, compatibility tool maintains what is done in CUDA, but you can do the things in a better way, for example, with events. And we will have a closer look on doing this in a few slides. Another difference between CUDA and SYCL is how you specify how many kernel instances are actually executed by the hardware. So the runtime and hardware need some information on how many instances you want to execute. And then CUDA, the way to go here is kind of, yeah, from my point of view, hardware oriented. So you specify the number of threads per block, as it is often called, which is basically the number of concurrent kernel invocation in a block. And a block is a logical concept that finally maps to a streaming multiprocessor within the GPU. And so you specify the number of threads per block, which is kind of, yeah, as I said, close to the hardware. And you also specify the number of blocks you want to execute. And what you usually do in your code is that you derive these numbers from your actual problem size. So the number of threads per block, you often do in an educated guess, or you use magic numbers, as we will see in a bit. And then you divide this by the problem size to get the number of blocks you have to use. So in that way, it's a little bit, yeah, I would say cumbersome for the programmer, but it is closer to the hardware. In SYCL, the things are again a little bit different. So here you have a more domain-oriented way to specify the number of work items, as they are called here. So the number of kernel instances, so to say. And you basically specify how many work items you want to have. So how large is your problem you want to solve, basically. However, you also have the option to group work items into so-called work groups. And this is similar to to the concept of the CUDA block size, so the number of threads per block. And there's a data type named ND range in SYCL, which allows you to specify both the overall size of your problem and then the, let's say, hardware-specific workgroup size. And this you can put in together in a so-called ND range and pass it to the parallel for function here to execute a kernel on a particular problem size with a particular workgroup size. And if you migrate from CUDA to SYCL or DPC++ with the compatibility tool, you have to be aware of magic numbers that you are used to in CUDA. For example, 1024 threads per block is a number that you find very often. I think the compatibility tool warns you about some numbers, but be aware that sometimes it's not the case, and you usually should query your device, which is a good number for workgroup size. That would be a platform independent way to specify the workgroup size. There are other differences as well when it comes to error handling and timing. So for error handling, you have in Cuda this C-fashioned like checks for return value. So often you write preprocessor macros to check if the return value was an error or not, and then you bail out and terminate your program in case an error occurred. And in SYCL or DPC++, things are different. You have exceptions. And the compatibility tool assists you here again, and it migrates between these two approaches. So it recognizes even preprocessor macros that are defined by yourself and rewrites them in a particular way and generates try except blocks for code snippets where such checks are made and exceptions are returned. When it comes to timing, in Cuda, the best practice is to measure kernel execution is to use events. As we have seen in the easyWave code, we use events, or it uses events there as well. And for the compatibility tool, as I indicated already, code is generated that relies on wait calls to synchronize with the device or synchronize with the execution of a kernel. And then it uses std chrono clock methods to measure the time that it took for the kernel to launch and execute. And that way it measures the time for executing the kernel. However, as I said, you can, or introduced, give you the promise in the introduction that you can be more SYCL-esque. You can do better than this. So as I said, the compatibility tool won't magically do everything for you. It is a generic tool, so it recognizes certain patterns, so to say, certain operations that you're doing, and it does in some instances surprisingly well from our perspective. However, as I said, the migrated code is only a starting point for further optimization and changes. In case for easyWave, we had almost no things to change to get the code actually compile and run on a device after the migration process. But it doesn't mean that other applications need adjustments after the migration process. And even after the migration process has finished and your code compiled, you want to improve the code quality usually. And I want to name a few things here, and we'll give you a brief example afterwards. One thing you may think of is that you change the memory management. So as I said, the compatibility tool generates code that looks quite similar to what Cuda does, so with explicit memory allocations and transfers. And as I said, this is a good thing if you're used to Cuda or C and so on. However, if you want to, you can switch to SYCL buffers and accessors if you need this. So, and I think this is really a point of personal preference. However, it also enables you to have implicit dependencies between kernels or command groups, to be more precisely. But this relieves you from manually handling the kernel dependencies. But as I said, this is a kind of personal preference how to go here. And if you don't use SYCL buffers or accessors, and you use unified shared memory, and you continue the usage that was introduced by the migration tool or compatibility tool here, you have to use events to explicitly specify the dependencies. You then can also use these events independent of whether you use buffers or not, or USM or not. You can use events for timekeeping, and you can also make the kernel invocation a little bit less verbose than it was generated by the compatibility tool. And what you should also do is to query device properties, like for example, the workgroup size that I mentioned before, and other parameters to get closer to what the hardware actually performs and to be more platform or device agnostic, or to support a larger variety of hardware here. And what you can also do, if you want to, is you can replace functions that are used by the compatibility tool from its own. It uses functions from its own headers to manage things like two-dimensional memory allocations. Maybe there are sometimes not direct equivalents to these operations that you find in Cuda in the SYCL standard. And for these purposes, I think there are the headers from the compatibility tool. Maybe you want to be independent of those, and then you have to, kind of find an other counterpart for these functions on your own. But I think this is not an actually showstopper here to prevent a successful further migration process. Okay, now let's have a look on how can we a little more SYCL-esque, as I call it here. And as a starting point, we have a sequence of kernels that depend on each other, and this is actually something that we got out of the compatibility tool process here when we fed it with the easyWave code. And easyWave has a sequence of kernels that is invoked, and this is basically what you get out of the compatibility tool in such a case. So you basically have a submission of a kernel that you depend on, and then the compatibility tool, as I said, generates functions, a function called to wait for that kernel to finish. And then we want to launch another kernel. We use another queue submit operation here and specify a command group and so on and so on. Specify the problem size and actually launch or invoke the kernel function here. And we do a timing measurement around this kernel invocation. And since we use a wait call here again, we can be sure that the kernel has finished. And so we get can get the timing for this particular kernel execution. And now we want to do this a little bit different and maybe a little more the way that it should be written in a SYCL way. And the first refactoring that we used to do here is that we make use of the events that are returned by the queue submit operation to define dependencies. So as I said, the submit call here returns an event which can be used to define dependencies. And we use this event that is returned here inside the next command group for the next kernel we want to execute and specify that we depend on this event. We can also specify multiple events, but for brevity, I just show you one event. And we can also use this event then to wait on the kernel to finish. So this is basically this call on the bottom here is basically just an explicit wait call on the return value that we got from the submit function here, and before that we had just a wait call after the function, which is basically the same. However, we can use the event now to do the timing of the kernel, and we can then also be a little bit more precise, since events not only cover kernel execution but also cover kernel submission time. We can also check for how long the kernel waited before the execution started. And so we get an event out of the queue submit operation, as I said, and then we wait here to ensure that the kernel is actually finished. And then we query profiling information from that event to determine how long it took to execute. However, to do so, the queue that we are using here has to have profiling information enabled. You basically just have to add a line when you use or when you create a queue object here, but you have to use this or have to do this before you can actually execute this or query this profiling information. And then you can actually shorten the kernel invocation. So you can get rid of all this command group handling stuff, and you can just say, I want to do a parallel for operations with this problem size and kernel dependencies here. And you wait for the kernel to finish after that. So by that, we reduce the kernel and timing measurement code and so on quite a bit, and it's less verbose, and I think it's more clearly what is going on here, and that's a way to be more SYCL-esque for this particular code base. So now we have a nice code base maybe that is SYCL-esque and looks good, and maybe you optimize this, and now we want to look on how can we actually use different architectures. For Intel processors and graphic devices, this is very easy. You can just fire up the data parallel C++ compiler, and then you can use the same binary that comes out of this compilation process and run the binary on different devices. And to control which device is used, so if you don't explicitly use GPUs or CPUs in your code base, you can specify which device is used via environment variables here. And by doing so, yes, you use the same code base, as I said, and can just switch between devices easily. And we were successful in doing so for core processors or notebook processors with integrated graphics, so Gen 9 graphics, but also for the pure CPU side, so to say, and also for Xeon processors. And we were also able to run the same code base on a CPU as well as a GPU like Gen 12 or the DG1 GPU here. And then some interesting possibility arises. So with the code base that you now have, and if you are platform agnostic, so to say, as we were in easyWave, you are able to compile for an FPGA. And you do this with the data parallel C++ compiler again. So if you're used to FPGAs, you usually write VHDL or some other high-level hardware description language. And then you have the process of generating bitstream, programming the FPGA with that bitstream, and so on and so on. And this is basically all hidden, mostly hidden when you use the OneAPI toolkit here. So you can just fire up the data parallel C++ compiler with some flags to generate code, so to say, for the FPGA hardware. And the only thing you have to do is to have time, because this takes some hours in our case to actually get a bitstream out of it that is able to execute or run on the binary that you can run and start, and to run it on an FPGA. This hasn't changed. If you are a VHDL developer, you know this, that it's time consuming to actually get a bitstream, but you don't have to deal with VHDL or other languages here. So this is really a good thing. You start with C++ code, with SYCL code, and you get the possibility to run code on an FPGA. And even for execution, you don't have to hassle with bitstream uploading and so on. This is done by the binary in the runtime environment. However, in our case, this is a little bit limiting, because we want to control actually which kernel or which version of a kernel is executed on a particular device, especially for an FPGA. But I think this is will be supported in the future, or at least we hope that this will be supported in the future. The only thing or requirement that is required to execute on the FPGA is that you have to have a board support package, so which is compatible to OneAPI OpenCL, this is a requirement to actually run the binary then, or execute code on the FPGA. However, you can save time. You don't have to go through the compilation process, which take hours during your development process. You can use an FPGA emulation that comes with OneAPI toolkit here by default. It runs on the CPU at CPU speed, and it basically just executes your binary. At least this is our understanding here. So it appears to be a native SYCL execution of the generated SYCL code, or so the compiled SYCL code, so to say. But it may have some differences between your emulation on the CPU and the real FPGA. For example, if you use particular data types, or you want to use them, and the CPU is not able to mimic them in a 100 compatible way, then you may experience problem or differences between the FPGA and your CPU. And the same thing applies to atomics maybe. At least we had problems with that in the past, so we had to ship around some issues here. However, you should refer to the documentation to spot differences between emulation and real FPGA execution. However, as I said, this is really a great opportunity. So even if you don't used to FPGAs, you can now go ahead and program FPGAs, even if you are just, in quotes, a C++ or SYCL programmer. So in the past, this field of devices, I think, was kind of limited to developers that are very close to hardware. And I wouldn't say that you don't need information about this hardware architectures in the futures, but it brings FPGA, I think, to the masses and allows programming those devices for a larger community. Although, if you really want to program for an FPGA, your SYCL code would still look different from a generic SYCL code. You still have to do adjustments to get optimal code that runs best on your FPGA. Coming back to our original code base, actually, so we started from Cuda, and now we have DPC++ code that runs on CPUs, GPUs from Intel, and FPGAs from Intel. The question was, can we actually reuse our Cuda hardware? And yes, we can. So if you remember that DPC++ is basically SYCL plus some extensions, which are now partly in the standard as well. The only thing, so only in quotes, that you need to migrate to a new platform is the SYCL implementation. And luckily, CodePlay, so the company from Scotland, I think, contributed to the open source Intel LLVM compiler. And you can download that compiler and build it with support for Cuda devices. And with that compiler, you can then actually compile your DPC++ code for Cuda devices. And you are able to execute this code on your Cuda hardware again. So you don't lose, you don't have to throw away your Cuda hardware. You can still use it. You only have to specify some environment variables, but that's it after the compilation process. And the good thing is that you don't lose your ecosystem as well. So you can still use NVIDIA tools like profilers. I have used this actually, so it works. And you can also use debugger, but I don't know if that really works. So, but it looks promising here. So overall, I would say that the compatibility tool really assists you in an otherwise tedious migration process. So you can get easily from Cuda to Data Power C++. However, you will still have to do some tweaking and tuning of your code base. So as I said, it's a good starting point, but if you really want optimized code for other devices than Cuda devices, for example, or be more elegant and have support for a broader range of devices, you have to adjust your code base. This is something that the compatibility tool won't relieve you from. And although that there's a lot of similarities between Cuda and DPC++, you have to know that there are some subtle differences, and you should refer to the SYCL standard and be familiar with that if you intend to migrate away from Cuda to Data Power C++. However, if you do the migration, it really pays off from our perspective. So you gain support for multiple platforms like, as we have seen, CPUs, FPGAs, and also your familiar, your good old NVIDIA device here. But then you are not bound anymore to a particular vendor hardware or vendor language, so to say. But you are now able to use open standard like SYCL to compile for different architectures. With that, I would say thank you for your attention. Here are some references for further reading and some other resources. And I think the slides will be available, so you don't have to copy paste them now or make a screenshot. I think the slides and the presentation will be available shortly after this talk. And with that, I'm open for questions, and I think some are already on the chat. Thanks a lot.
Thank you very much, Steffen. So Nalini, if you could unmute your line to please moderate the questions.
Yeah, so there are a couple of questions. I think I answered a couple of them. And then, Steffen, thanks first of all for this great presentation. We really appreciate what you've done, and having you come and speak about this also gives other people a starting point to see how they could do this. Okay, so a couple of questions here. So first is, what would be an optimal way of using measuring events without weight? In other words, how could you measure the events for a kernel in an asynchronous manner?
So if I understand the question right, is how you can omit this wait call here?
Yeah, I think that's what they're asking. How do you remove the event wait?
Yeah, okay. So in principle, you have to be okay. So if you query profiling informations, which includes informations like when the event has finished, or the command group finished, or the command group started, you actually have to wait for the event. So there is no other way to get around and to get proper timing information without that event call. However, I think the question, what my point was in this talk is that you can remove all the sequence of wait calls here, which is maybe not a good thing, since you always have the synchronization overhead with the device maybe. So in that sense, you can get rid of this upper event wait call by specifying the dependency here, and that way you don't have to actually wait on the host side for the device. So I hope this answers the question. Yeah.
Yeah, I can add something as well. I think there are no event callbacks yet in SYCL, but I think in future versions there will be like event callbacks like it was in OpenCL.
Okay, thanks. The next question is, how much effort is it to do this CUDA to SYCL and then get performance?
Okay, good question. So actually, for easyWave, this migration process is quite effortless. So as I said, you can just use the migration steps that I've shown you here, and then you have to fix some minor issues in the code, and then you have a code base that actually compiles, and compiles for CUDA hardware as well. And I don't have shown you the numbers here, but we made some experiments, and with the open source compiler and its support for CUDA devices, we end up with only 4% of performance. So we only lose 4% of performance, which is not that much. I think it's more or less identical in the case of easyWave. So the comparison between original CUDA code and the DPC++ code that was compiled for a CUDA device. So basically, in our case, we didn't lose any performance. However, that doesn't mean that you have to tune your code for other platforms. If you want, for example, a better performance on a CPU, then maybe the migration process is not a good thing, because the original code base was written for a very powerful data parallel architecture, so CUDA in this case, and your CPU may not fit to that very well. But you have to consider that depending on your actually code base.
Right. Okay, let's move on to the next one. Do we need a different binary executable for heterogeneous environment with some or all of CPUs, GPUs, and FPGAs? If yes, is there any way to decide at runtime which executable is needed? So, I mean, of course, you need a different binary executable, but is there any way to decide at runtime which executable is needed?
So for, as I said in the talk, for Intel GPUs and CPUs, or maybe it wasn't that clear, but for Intel GPUs and CPUs, you can actually use the same binary.
Yeah, but not for FPGAs, right?
Yeah, exactly. I think for FPGAs that won't work. So that would be really nice if you can just use your compiled binary that is generated in a couple of seconds for an FPGA. So that won't work. And I think the reverse way won't work as well. So if you compile for an FPGA, then that would not execute very well on a CPU or a GPU. But maybe Marius can fix me if I'm wrong here.
Yeah, so I think it's possible to combine like the bitstream for the FPGA in the host binary, so to say build a fat binary, and then using the selectors in the host code to select the device.
And maybe I can just add for the, actually I haven't tested if I didn't have the idea to run a binary that was compiled, for example, for Cuda hardware on a CPU that is supported by Intel, so to say. But I wouldn't expect it to work. I haven't tried it, but I wouldn't expect it to work. And then it's a really good question. And maybe some Intel engineer can pick this up and yeah, escalate it in case this is a valid use case.
Okay, next one, is the call queue submit wait call asynchronous from the host?
So the question is if this queue submit and then in wait call is synchronous on the host.
Yeah, is it asynchronous from the host side? Yeah.
Asynchronous?
Yes.
Okay, okay. So yeah, you have to distinguish here, I think. So the execution of the kernel here, or the command group to be more precisely, is more or less asynchronous to the host, but the submit operation is not. But if you want to wait for the kernel to finish, you have to issue this wait call, and then you are sure that the kernel, that the work that you have specified in this command group has finished.
Okay. Have you done any experiments? Nice talk. Have you done any experiments with SYCL on AMD GPUs? If so, how different are SYCL and DPC++?
We don't have made any experience on AMD GPUs, but we are aware that there is an implementation, I think it's named IXPUG, if I'm not wrong, from University of Heidelberg in Germany, that wants to support one API for AMD GPUs. So, as I said, we don't have experience, but I think it's in the making, if not already available.
Okay. Thanks, Steffen and Marius. This is a great talk. I know we couldn't get to a couple of questions. I will forward them to Steffen, and we will get you the answers. We're on top of the hour, so we end the recording here. Thank you, everyone, for attending. Look out for our next talk, which will be sometime in March, and the recordings and slides for this will be available on the IXPUG website.